it is. So that's to put things in perspective. I'll now talk a little bit about thermoelectrics themselves. I'll start with the generally used and admitted equation for the energy efficiency of a thermoelectric. I don't know how well you can see at the back. Can you read this word at the back? Who can't read this word at the back? All right, it doesn't matter. It's not an eye test, but I just want to make sure that I'm able to communicate what I'm saying. So the interesting thing about the energy efficiency is it's made up of two terms. This term here is just the Carnot efficiency. And the next term is the materials characteristic for the thermoelectric, and it's generally expressed in this parameter ZT. This is often seen as a figure of merit for a material, but you can also recast it as a figure of merit for a device. But if you go to a materials textbook, they won't tell you that's for a device, but it's very similar for devices for material. The important thing is it's a contraindicated parameter, by which I mean that it increases with the Seebeck coefficient squared times the electron conductivity, and it's divided by the thermal conductivity. And what makes it contraindicted is that the thermal conductivity consists of the heat that's transferred by electrons. So that's proportional to this term. And it's also proportional to heat conductivity by phonons. And so this is just a rather standard plot. And it shows that for a standard type of semiconductor, as you increase the number of electrons, the Seebeck coefficient decreases. Remember, you need this squared, so that's important. At the same time, the thermal conductivity goes up. That's because of this electronic contribution. And so, and lastly, of course, the resistivity goes down. So there's an optimum value for, in this case, carrier conductivity concentration in order to maximize ZT. So what this expression really tells you is you want to maximize this power factor. That's the product of Seebeck coefficient times the conductivity. And you want to minimize the thermal conductivity because it's in the denominator. So let's look at some of today's best thermoelectrics, if you could buy them. Most of them you can't buy, but never mind. So this is our friend ZT as a function of temperature, and because this is done by physicists, it's in Kelvin. There are two things to note about this. One is these curves typically rise, reach a peak, and then decrease again. That's because of the way in which the electron conductivity increases with temperature. So you'll see that there's a whole range of materials that have ZT of less than 1. Those are the old materials. And then there's a whole class of materials that I'll call new, and I'll explain what I mean by that soon. But you'll see in most of those, the characteristic ZT goes up and then stops. The reason they stop is most of those materials melt. So 600-700 degrees Kelvin is the maximum temperature you could ever use these materials. So by my definition of what high temperature is, we automatically can discount those. But nevertheless, these are important factors. The other thing to note about these is that these materials, the ones that you could use that I'll call the old materials, contain bismuth, tellurium, selenium, number of other chalcogenides. And furthermore, many of these elements, if you go further up, can be quite rare, like ytterbium, antimony, are really rather rare. So these are remarkable materials, and there's been tremendous advances for thermoelectric coolers in the development of these materials that can be used at a moderate temperature. But they're often scarce elements, they're often toxic, and the high ZTs, as I'll describe in a minute, are really due to manipulation of the microstructure. And that's important for reasons I'll describe. So what we really need, as I mentioned before, and I'll try and justify now, is compositions that are based on more common elements and that don't depend on microstructural refinement. So let's step back a bit. Where obviously elements come from the Earth's crust. So we can ask, what are the elemental abundances in the Earth's crust? So this is a plot. It comes from the United States Geological Survey. It's a logarithmic plot as a function of the atomic number. And this number here refers to the number of atoms of element for every million atoms of silicon. So here's silicon. There's a million atoms of silicon there. Calcium, magnesium, sodium, they're fairly common. If you look at tellurium, 10 to the minus 3, so for every silicon atom, there's 1/billionth of an atom of tellurium. I'll put it away another way because we can't split atoms. You get 1 atom of tellurium for every billion atoms of silicon. Similarly, you can look at bismuth, you can look at silver, antimony, cadmium. Many of these elements you wouldn't necessarily want to use, but even if you could, they are fairly rare. Now, this is one way of representing abundances. They just tell you that they're in the Earth's crust. They don't tell you where they are or how easy it is to get them out. And so one way to express this is in a language that's borrowed from the financial community. And this is a global supply risk. So if all your elements come from one country and you're not very friendly with them, it's not going to be very easy to obtain the elements, or they may jack up the price. So this can be expressed in terms of a market concentration by this Herfindahl-Hirschman index, the HHI. And this is the definition. By the way, the percentage doesn't go from 0 to 1. It goes from 0 to 100. So you can get very large numbers. I won't ask you to read these because we have a better way of representing it. That is with these diagrams. This is work we did with our colleagues at Santa Barbara. And this is obviously the periodic table. And each element has 3 colors associated with it. One is the abundance. It's the bottom one of these triangles. And then there's the HHI index for production and reserves. The important thing to take away from this is that the scarce materials are in red, and the abundant materials are in blue with colors in between. So I don't mean to pick on tellurium, even though we've worked on it for some time. You can see that it's a very scarce element. And the reserves are very low, and the supply, the production is even lower. So just visually, you can see the elements we want to use are these sort of elements. They're the ones that are abundant in the Earth's crust as well, by and large. So that's why we want to think about these materials. And the other point is, for off-grid large applications, for instance, just take the example of an exhaust of a car. There are millions of cars, tens of millions of cars on the road. If you were to implement it, each of them, you're going to need a large volume of materials. So that's another reason for thinking about compositions that are made of abundant materials. And this is new in the sense that up till now, the materials community has not really worried about resources. Certainly it's true in the last century and the century before. You'd find copper in the ground, you go to mine it, and all the effort was on efficiently mining it. But there was never this restriction of resource. More recently, gallium has been one of the materials you have to think about it. But it turns out that gallium comes when you mine aluminum. So as long as there's adequate supply of aluminum, you can get adequate supply of gallium. The other thing you can do with data mining is to try and identify which sort of composition should you be working on if you want good materials. So this is a rather complicated graph, but it's a plot of the Seebeck coefficient, and we either want a high negative or high positive value as a function of resistivity for all the materials that we could find in the database, and that's several hundred different compositions. The ones with the big circles are the ones that have a high power factor. And what you want to be able to do is have ones that are on these parabolic curves. Material out here, this includes some of the materials I've worked on, by the way. There's no hope of using those in real practical applications. They might tell you something about underlying physics. But the reason you have to use this sort of approach together with, if you like, the abundance is that almost all compounds are thermoelectric. In fact, it's often used, or was used in the past, to measure, you'd measure the Seebeck coefficient to find out what the defect concentration was, for instance, in a semiconductor or a ceramic material or inorganic material. So you have to do studies like this. So let me now address this issue of microstructural evolution. I've really just mentioned, now I want to give you a little bit more of a context for it. This is a plot of ZT as a function of year of discovery of different thermoelectric materials. It's rather sparse because I just want to make a point. Until about the 1950s, 1960, silicon germanium was the material of choice. This was a solid solution of silicon germanium. It could be cast into large pieces. And this is what was used in the space programs. So you attach this to a radioactive source. As the radioactive source, the radioactive species decayed, it would warm up. That would create one side of a junction to create electric power. It could operate in deep space. Then bismuth telluride came along. And then you see that there's a sudden jump around the 1990s. I'm going to say that's the area where the nanostructuring era began. I'll explain that in a moment. And from that point of time, we have a whole series of different compounds. And, of course, people have started working on oxides. But as usual, there's a bit of a lag.